and gentlemen. This is Alice. I'm going to, chair today's ICANX talks for the first part of our welcome. And this is Alice from Peking University. Actually, I'm so excited tonight. Yeah, I couldn't wait till 8 p.m. at Beijing. So, hello to everyone, no matter where you are. So this was a very special day, and because in China today was May 20th, May 12th. So it's our Earthquake, memories day. So that was 15 years ago. So it's a big day in China. And but today in our ICANX is also very excellent day. Because ICANX this year, 2023, we're going to have invited, thousand scientists from 100 university, and are going to have more and more people get involved. So we have started a new channel as Youth Talks, and every Tuesday we have this ICANX Talks as every Friday. Friday, this was invited all the top scientists from all over the world. And the Tuesday one is going to invite the young scientists from everywhere. So we're going on very well. And we have this year's schedule for ICANX Talks on Friday. See all these people here, and it's on schedule, very good, and everything moves so smooth. All this was thanks to all my colleagues. This was our great team for the moderator of ICANX. So it's me, Paul Weiss from UCLA, Fulan from Australian National University, Martin Suhr from Iowa, not Iowa, sorry, but he's not in North Carolina now, and Kristen was from University of Twente, Europe, and Mischa was from SKKU and so. So ICANX will go out so well because all these people are working very hard, and all the scientists was contributed very excellent. So we're going to move forward like this year. We have big plan, so we need more people to jump in. So today was a special. So we're going to welcome our new partners. First, let's welcome the lady. Yeah, so Professor Chen Rong from Huazhong University of Science and Technology. Rong was get on the stage several times. He delivered her talk, years ago, like it's last year. And he's a super, scientist in China, especially, a female young scientist, was excellent. He won numbers of prestigious awards. A graduate from China University of Science and Technology. I got her PhD from Stanford University. Back to China to Huazhong University of Science and Technology. And she is a leader scientist in nanofabrications. And she done a lot of nice works, and she also a very good leadership in this. He was chairing several of the this big conference, and he is the superstars for leading the science projects, and he win. I see that numbers of prestigious awards. So we're really happy to have Professor Rong here. Welcome, Chen Rong. And we have our next, new partners is Professor Paulo Samori, is from University of Strasbourg, France. And maybe many people already know Paulo. Paulo gives the talks on ICANX last year. Super nice work, amazing. Get a lot of attractions. And Paulo also win many, prestigious honors, and also he's members of several academics. So Paulo, the most major thing is he was the director now for a very outstanding or unique institutions. Your institutions was done a lot of work in nanofabrications, in this nanoscience and technologies, not only from a chemical part, chemistry part, also involve a lot in the energy part and in the sensors and actuators. So as a pioneer in this world, so Paulo also gave us a lot of hands to invite all these speakers, to today the speakers, is Paulo's good friends. So yeah, we are so happy to have such a nice, group, everyone to working together. And now ICANX is having you know, very qualified, moderator team. We have boys and girls, right? Yeah, we have from different part of the whole world, cover different part of the topics. I think it's very very happy to have all these peoples working together to make ICANX moving forward to can host many different speakers in different field. And I'm so glad to introduce my new partners. I welcome both of them to join this great team. I hope, we can get more things to do. And during the panel discussion part, we also have time, chance to discuss all this. Now, without further ado, I think, Paulo, it's your time to chair the session today, please.
Thank you very, very much, Alice. So it's my great pleasure to join the team as a moderator. So it's a great team, actually, from all over the world. And I actually in this super great initiative organized by Alice that is really going and presenting very well and presenting groundbreaking science all over the world. So this is really a success of open science, is a success of ICANX. So now today what we have is an amazing speaker. So we have actually Professor Mischa Bonn. Professor Mischa Bonn, he is a Max Planck director. He joined Max Planck Society in 2011 as one of the directors of the Max Planck Institute for Polymer Research in Mainz, in Germany. And he is actually heading the division of molecular spectroscopy. So Mischa actually carried out his master. He's finished his master in physical chemistry with highest honor in 1993 at the University of Amsterdam. And then he carried out a PhD that he finished in 1996. This was done in a FOM Institute for Atomic and Molecular Physics in Amsterdam. And then he carried out 2 postdoc stays. So the first postdoc was in Germany at the Fritz Haber Institute in Berlin. And then later he had a second postdoc in US at Columbia University in New York. Then he came back to Europe. He got an assistant professorship at Leiden University, and he got the tenure, and then he got the promotion to associate professor. Then in 2004, he went back to Amsterdam at FOM Institute, and he was group leader. And then he has been extraordinary professor since 2005 at the University of Amsterdam, and honorary professor at Mainz University from 2012. Essentially in parallel to his directorship of the Max Planck Institute in Mainz. So he serves as the deputy director of Journal of Chemical Physics, and he's also a member of the editorial board of many journals, for example, of the Journal of the American Chemical Society, so the most prestigious chemistry journal that you have from the US side. And so he received many awards for his groundbreaking work. And so I can just name 2 of them. The gold medal for the Royal Dutch Chemical Society, and the Van Hoff Award that is given by the German Bunsen Association. So that is really a label of excellence, of proving the outstanding type of science that is carried out by Mischa and his group. Now, indeed, Mischa is interested in the development and application of laser-based ultrafast spectroscopy to advance the understanding of natural phenomena in particular at interfaces, and frequently this involves the molecule that is at the very heart of Mischa, that is water. So actually water is nothing else than the topic of the today talk that is entitled the Water-Graphene interface, a Quaint quantum couple. And so Mischa, the floor is yours, and we are very much looking forward to hear from you. What is this miraculous molecule named water?
Thank you very much, Paolo. It's a very kind and generous introduction. And I hope you can see my screen now. Yes. So wonderful. And thank you also for the opportunity to be here and share some of our research with you. So I'm going to talk about a very peculiar couple, namely graphene and water. I think many of you know that graphene is peculiar, but I'll show you that water is also peculiar, and when the two meet, interesting things happen. But before I tell you about the research, I have to thank this wonderful group of people. So the surface spectroscopy was primarily done by Yong Kang, and with help of Taka and Yuki. And the graphene water friction that I'll tell you about was experimentally done by Zhao Qing, and the theory was done by Nikita. Okay, let's look at water. So water is central in biology. It's central in corrosion science, in material science. And typically we think about water as a continuum. So it's a continuous liquid with a certain viscosity, a certain density, a certain dielectric function. And that description works very often, but it must actually break down when we go to interfaces and when we go to the nanoscale. And so if we look at natural phenomena, like this is a protein called aquaporin, where you essentially have a single file of water molecules, and it's clear that we cannot describe this single file water molecules with a viscosity or a density. Those bulk concepts simply don't apply anymore. The same is true in the environment. If we look at water interacting with surfaces, that interaction is really molecular level details matter. If we go to technologies, if I want to desalinate water, it means that I have to create pores that are small enough that water molecules can come through, but not the ions. And I'm again in a similar situation that I am in this aquaporin. And finally, if we want to split water into hydrogen and oxygen, it's clear that that is an effect that cannot be described by continuum models. And so interfacial and nano-confined water is important, but it's very poorly understood. And this is what a lot of our research is aimed at, is a better understanding of molecular properties of water. And today I want to focus on a very interesting water surface, namely the water-graphene interface. And I will tell you two short stories that were both a little bit unexpected. One is where we have proton tunneling through the graphene water interface. And the other is the story of when water flows along graphene, what is the nature of the friction that the water experiences. And I'll show you that in the first case, there's tunneling occurring. And in the second case, I'll show you that quantum friction plays a role. So there are really quantum effects that affect the macroscopic observations of processes occurring at the graphene water interface. All right, let me start with the first topic, the proton tunneling. And so the motivation comes from the realization a little bit that water is a very strange molecule because it has a gigantic dipole moment. So the partial charge on the oxygen atom is almost 1 negative, and of course the counter charges on the hydrogen atoms must be half of that each. And that means that there's a gigantic dipole along this axis here. And so there's a very strong response to charge. That is one aspect. So if a surface is charged, it will align the water molecules. The second consequence of this charge distribution is that there are these very strong intermolecular interactions between water molecules. So we call them hydrogen bonds between the hydrogen on one water molecule, and it's just electrostatically attracted by the oxygen atom on the other water molecule. And these very strong interactions, actually, one can show, give rise to many of the anomalous properties of bulk water. So one important question that the community of people that study interfacial water like me have is what happens when you charge a surface and the surface has a positive charge or a negative charge. And so if there's a positive charge, it's kind of intuitive that the positive charge would align the water molecules with their hydrogen atoms pointing away. And so you would have alignment of the dipole of the water relative to the positively charged surface. It's not so clear what happens when water is negatively charged. So there's two things that can happen. Of course, we can again have dipolar alignment of water, which is then pointing down towards the surface with its OH groups. But you can also imagine that the water, the way it interacts with other water molecules, would like to hydrogen bond. And so you have OH alignment. And it was not quite clear whether this asymmetry, this asymmetric response of water to differently applied fields, how that works. And so that means that's the question we wanted to answer, and we were going to use graphene as an electrode to have a charged system, and I'll show you that surprising things happen. But this was the original, very fundamental question that we asked. Now, if we're going to charge a surface, we're going to have to be concerned about possible electrochemistry that is happening. And so if you have any electrode, like a platinum electrode, and you apply a negative charge, what can happen, of course, is that protons from the water can suck up those electrons, in this case, the platinum, and two protons can recombine with two electrons to form hydrogen. And you have the hydrogen evolution reaction, which occurs at increasingly negative electrochemical potentials. And in this case, you can see the hydrogen bubbles appear. And so you have zero current at high potential. And then as you increase the negative potential, at some point you get a macroscopic current and you get hydrogen generation. Now at positive potential, so if we zoom in this region here and at higher potential, what you see is now that, so this dot here now is this whole scale. So you see that there is also a current running as we apply a potential. So this is cyclic voltammetry, and that has to do, that's what's called a capacitive current. So here we have an electrochemical current. Here we have a capacitive current. So we apply a certain potential. The potential is not big enough to run a reaction, but it is big enough that ions, counter ions, absorb to the surface, and thereby a small current can run. And what is important is that you note the difference in the scale here and here. So here we're talking about milliamps per square centimeter, and here we're talking about microamps per square centimeter. If you look at an electrochemical textbook, you will find that this is described by electrochemistry, and this capacitive region is described by physics. So it's described to ion adsorption and dipolar reorientation. And of course, when we were asking our question, how does water respond, we want to be in this, let's say, physics region of the IV curve. So we don't want to apply two negative potentials that are too negative that we can drive chemistry. So let's go back to our questions and realize that in order to do this particular experiment and charge the graphene surface, of course, we need to do that with an electrochemical cell, because we can't just have a floating potential that would not be defined. And so what we did is we built an electrochemical cell where graphene is the working electrode, as you can see here. The graphene is supported on calcium fluoride because we want optical access through this window to the graphene water interface. And looking from the top, this is essentially what the electrochemical cell looks like. So we have our working electrode is the graphene, and then we have a reference electrode and a counter electrode. I don't want to go into all of the electrochemistry, but it's just to show you that we've done our homework and we can now apply controlled potential to the graphene. And so, as I already said, this design allows us to access this graphene water interface here with a set of laser beams that will allow us to interrogate the water that's specifically, basically the one molecular layer of water that's specifically interacting with the graphene. So how are we going to do that? Well, we're going to use the vibrations of water molecules. So water molecules are very happy units. They like, they're cheering all the time, essentially. And in fact, if there are other water molecules nearby, their cheering slows down a little. So the vibrational frequency of this OH stretch mode right here is a very distinct function of the hydrogen bonding distance and thereby the hydrogen bonding strength. So we can correlate the oxygen-oxygen distance or the hydrogen bonding strength with the frequency of that molecular vibration, which is expressed in wave numbers. So the stronger hydrogen bond means that this bond is essentially weakened a little bit and that the vibrational frequency is lowered, and that's what you see here. So stronger hydrogen bond, lower vibrational frequency. And so the OH stretch vibration is a very good marker of the local water environment, and this is what we're going to use. So how are we going to look at that one particular monolayer? Well, we're going to do that using this technique called sum frequency generation. And so that gives us the vibrational spectrum of just one monolayer of water molecules, even if that monolayer is on top of a bulk of water molecules. And in this technique, we come in with an infrared pulse that makes the water molecules very happy and oscillate at the surface. And then we can upconvert that polarization with a visible pulse. Here's the energy scheme to generate the sum frequency of those two fundamental frequencies. And this is a spectroscopy, because when the IR is resonant with the molecular vibration at the surface, this process is resonantly enhanced and we get more of the SOG light coming out. It's a surface-specific spectroscopy because it relies on this second-order nonlinear susceptibility that I don't want to bore you with, but I just want to tell you that this second-order nonlinear susceptibility is non-zero at the interface, but it is zero in the bulk. And so this is a bulk-forbidden spectroscopy, and so the signal can only come from the outermost monolayer. And just as an example, this is an SOG spectrum from the water-air interface, so nothing to do with graphene. And here you see that there's, we actually measure the imaginary part of this susceptibility, and it can be positive or negative. And that is actually because OH groups can point upwards or downwards because the symmetry is broken, and that's what we see. And so you see here that there's a high frequency peak around 3700 wave numbers. And this is actually very close to the OH stretch frequency of water in the gas phase. And so we can assign this peak here to this free OH group that is literally sticking out of the water and is not hydrogen bonding to anything. And then we have hydrogen bonded OH groups here at lower frequency, and they are obviously oriented down, which makes sense because it's this group here and these groups here. So we see a few water molecules deep, one or two water molecules deep. And so this is just to illustrate how powerful this technique is in unraveling these water at these interfaces. And just to make that point even more clear, if we look at the bulk infrared spectrum of water, it actually looks very different. Of course, there are no free OHs because everything is hydrogen bonded in bulk water. And you can see that at the interface, because the symmetry is broken here, the hydrogen bonding motif is a little bit weaker than in the bulk. All right, so let's go to the graphene system. And so here is our, I've highlighted it for you because it's difficult to see, but we have CVD grown graphene, large area. It's actually very high mobility. We had some guests from the group of Andre Geim visiting recently, and they were very impressed with the mobility in our graphenes. That was very nice. And we can get macroscopic conductivity through the graphene with gold for the electrical connections. And so then we can do this some frequency spectroscopy as a function of the applied electrochemical potential. And we've used a wide range here, and I'll show you how we interpret these results. And so this was done all in 1 millimolar sodium perchlorate, but other electrolytes give you the same result. So what we see here is that the response goes from OH groups that are hydrogen bonded, that are pointing down at positive potential, to OH groups that are also hydrogen bonded, but are pointing up at negative potential. And we see this funny OH group, type of OH group that only appears at negative potential that is also pointing down. And this is a bit, this was a bit of a puzzle. So let's forget about this high frequency mode for now. Just let's try to get our bearings first. And let's look at the hydrogen bonded part of the OH stretch response. And that is somewhat intuitive. So if we have a positive potential here, we have OH groups that are pointing down away from the positively charged graphene. That's okay. And then when we have negative potential, we see that at some point the water flips, it turns upside down, and we see that we get sort of this type of orientation, which is also intuitive. But what is not intuitive is this negative high frequency OH that is weakly hydrogen bonded at negative potential. And so it cannot be this type of OH group here, because this will be hydrogen bonded to water molecules. So this doesn't make sense. And it can also not be this guy here because it has the wrong orientation. So we don't really know what is happening. So the other thing that is quite peculiar is that you see that there's a very strong nonlinear response to the applied potential. So there's a large signal here for the downwards oriented water molecules that suddenly flips to all the water molecules at the interface flip. And once they're flipped, they're kind of done flipping. And it seems very, very nonlinear, which one would not expect at these moderate fields. So was all very confusing. So let's take a step back and think again what we're looking at. So we're looking at water that is on calcium fluoride, and we're trying to charge the graphene. We're looking at water in contact with graphene on calcium fluoride, and we're charging the graphene, and we're seeing what happens to the water. But we have to realize, and this is work from the group of Min-Heng Cho in Korea, that if you measure the contact angle, which is a measure for the strength of the interaction of water on a calcium fluoride substrate, and you compare that contact angle to calcium fluoride with one layer of graphene on it, you will find that these contact angles are indistinguishable, which means that the water feels the calcium fluoride, because we know that graphene by itself should be hydrophobic, but the calcium fluoride is hydrophilic. And so the water somehow feels the calcium fluoride through the graphene. And so in other words, a monolayer of carbon atoms is not thick enough to screen the charges and all the other type of electrostatic interactions that might occur between the calcium fluoride and the water. And so when we apply charge to the graphene, we have to consider also the charge on the calcium fluoride in order to understand what is happening to the water. And so we know that we apply a surface charge on the graphene. We know that the surface charge on the calcium fluoride is also important. And we know that first order approximation, the total surface charge is given by the sum of that of the graphene and that of the calcium fluoride substrate. And the nice thing is that we can determine the graphene charge and the total charge independently. And so the graphene charge we can simply get from measuring the Fermi level of the graphene using Raman spectroscopy. And here you see the behavior. So this is the surface charge density versus applied electrochemical potential. And it behaves like you would expect. The charge increases linearly with applied potential. It crosses around 0 volts, so where you might expect it to be. Interestingly, I showed you before that the flip of the sign occurs at minus 0.4 volts and not somewhere between the green and the yellow. So that's already an indication that something is funny is happening. But in any case, we understand the charge, how the charge varies with applied potential on the graphene. Now, we can also independently measure the charge that the water feels. And it's a little bit technical story, so I hope you'll just take my word for it. So what we do is we change the electrolyte concentration, and thereby we can independently determine the overall charge that the water experiences. And so that is when we do that measurement, we get this gray curve here. And you see that this is much more like the nonlinear behavior that we observed. It's also, we see that the zero crossing is close to where we observed the zero crossing in the experiment. So we can now infer the calcium fluoride surface charge from the difference between the total charge and the graphene charge. And you see that undergoes a stepwise increase in surface charge density with increasing electrochemical potential. So this was a bit surprising at first, but I'll show you that it actually makes sense. So it means that the water response is dominated by this big change in the charge of the calcium fluoride and not by the change of charge on the graphene. It also means that there must be some chemistry occurring on the calcium fluoride because it can only change its charge density by protonation or deprotonation or adsorption of negatively charged hydroxides ion or desorption of those ions. So there must be chemistry occurring in our system. And in fact, if you think about it a little bit, that is not so ridiculous. Because if we negatively charge the calcium fluoride, I told you we can have the reaction of two protons to form hydrogen. And even if we don't see macroscopic bubbles, there could still be a little bit of this reaction occurring where we generate net OH minus ions. And so we increase the pH a lot, and thereby we can change the charge density of the graphene. So we can understand how the reaction modifies the pH near graphene, but then how does that affect the calcium fluoride substrate? So if I change the pH here, how does the calcium fluoride feel that pH here? Well, we know when we put graphene on calcium fluoride that there's always a few water molecules trapped between the calcium fluoride and the graphene. And that means that we have one or two layers of water here between the calcium fluoride and the graphene, and that if there's a change in pH on this side, it will also lead to a change in the pH between the graphene and the calcium fluoride. And the reason for that, I stole this snapshot of these movies from this paper here. And what you see here is a hydronium ion on one side of the graphene. Just imagine that the calcium fluoride is on this side. This movie explains how the pH can equilibrate between the two sides of the graphene. So here's a hydronium ion, and you see that this proton jumps to this water molecule here. So now the proton is straddling essentially the graphene interface. And when this proton now hops to this water molecule, we end up with the hydronium ion on the other side of the graphene to where it was before. And it's this proton that tunnels through the graphene substrate that allows this equilibration. And this actually explains our spectroscopy results. And so we say that water dissociation raises the local pH. And if that were true, then we should be able to reproduce our potential dependent results, which are shown here for 3 specific potentials, and then essentially do the same experiment but at a different bulk pH to reproduce those results. And what you see here are in red are pH dependent measurements with no applied potential. So it's an open circuit experiments where we show that for every specific potential, there is a pH that reproduces the data very nicely. And here you see precisely what we observed in the electrochemical experiment, that we start out with low pH, so 5.6, and then we get an inversion of the water because we go to high pH, and that changes the surface charge of the graphene. So how does that explain the high frequency OH? Well, what happens is that when the pH increases on this side, we get a proton that is transported from the side of the calcium fluoride through the graphene to the bulk water side, and that leaves an OH group. And that OH group will absorb to a positive site on the calcium fluoride surface, and that will cause a calcium OH group that is now pointing down towards the bulk water, as shown here, and is not strongly hydrogen bonding to other water molecules. So this now explains this negative potential. So we think we understand what is happening. So we understand this flip, which is due to the change in the calcium fluoride surface charge. And that surface charge is changing because hydroxyl ions are absorbing, neutralizing positive charges on the calcium fluoride, and that gives rise to these negative pH. So now you would say, okay, Mischa, that's kind of nice. It's all, you're looking at electrochemistry. Well, good for you. But the remarkable thing is that this pH change that I showed you, it goes from 5 something to almost 11. It occurs in a range where the electrochemical current is less than a microamp per square centimeter. So this is clearly the capacitive region of the electrochemical potential applied, where if you look at a textbook, there shouldn't be any chemistry happening. And so what we find is that there is an increase in pH by 6 units or so in this capacitive region. So it's really not true what some of the textbooks say, that there is no chemistry occurring in the capacitive region. And so when we saw this and eventually figured out what was happening, I called my good friend Mark Koper, He's someone you should invite here if you haven't yet. He's a wonderful electrochemist. And I told him, Mark, we're seeing all this chemistry occurring in what is nominally the capacitive region of the cyclic voltammogram. And he said, oh, that's wonderful. Because when we calculate the capacitance of our electrochemical systems, we typically find that there is some sort of capacitance missing. So what we calculate is always less than what we measure. And we explain that by what we call a pseudo-capacitance, so that there are small electrochemical currents. And so what we observe here is pseudo-capacitive behavior in the physics regime that is not completely physicsy. So that was the first surprise of the graphene water interface, was that there was electrochemistry occurring, which we could really follow very nicely because we were using graphene as an electrochemical electrode. So in the second part of my talk, I really want to talk about physics, right? Which was the purpose of my first talk, what we set out to do, but it turned out to be chemistry. But now I will just stick to physics. And it's about what happens when water flows along a graphene surface. And so generally speaking, it has become clear in the past, I would say 10 years or so, of this exciting field called nanofluidics, that if I have a carbon nanotube and water flows through a carbon nanotube, that is very different, that behaves very differently from water flowing through a garden hose. And so one of the pioneers of this field is Lideric Bouquet, who's a very happy guy. He's in Paris, and he and his wife, Marie-Laure, do these wonderful experiments where they quantify flow and friction of water through nanostructures. And Nikita developed a theory to describe that I will introduce in a moment. And then Xiaoqing did experiments to test that theory. All right, so when we have a liquid flowing along a solid, there is a thing that you can define, which is a slip length, which is basically determined by the velocity that the liquid has at the interface with the solid. And so the friction that you have is roughly proportional to 1 over the slip length. So when I talk about slip lengths, it's 1 over the friction. And so what people have found is that remarkably, if you make a nano channel out of graphene, the slip length is very, very long. But if you make it out of graphite, the slip length is order of magnitudes lower, which means you have a much higher friction in graphite compared to graphene. Now, to make things more confusing, or maybe equally confusing, is that if you use carbon nanotubes and you measure the slip length, you find that there's a very, very sharp dependence of the slip length on the radius of the carbon nanotube. This was work done by Lideric. And why is this strange? Well, graphene and graphite and carbon nanotubes are essentially the same materials. And so classical friction theory, which says, a water molecule flows across a substrate, bounces along that substrate, and that's how it transfers momentum, and this is what is causing friction. Classical friction theory cannot account for these humongous differences, because the roughness of graphene, of the solid, whether it's graphene or graphite or a carbon nanotube, which is just curved graphene, the roughness is identical. So we cannot have orders of magnitudes variation in the friction if it's just this classical collision type friction model. So Lideric and his group concluded then that something is missing in this roughness picture. And Nikita Kavokin, together with Marie-Laure and Liederik, then wrote a paper it's a purely theoretical paper, which was published in Nature 2 years ago. And they said, well, you can have physical corrugation on a surface and molecules bumping into that and transferring momentum that way, but you can also have electronic corrugation. And maybe there's electronic effects that give rise to the friction. And so what they postulated is, well, there's electrons in the solid, and there may be holes too. The water molecule has a dipole that can interact electrostatically with those charges in the substrate, and that can give rise to friction possibly. And so you can calculate an electronic friction force, which is essentially given by the surface excitation spectrum and the sort of surface response function and the properties, the dipolar properties of the water molecules that flow along the substrate. And so this is a whole theory that I don't want to go into, because I know, honestly, I can barely follow it. It's very complicated. It's very interesting. But let me try to summarize this theory in a simple way. So the friction force per unit area can be explained by a classical friction coefficient and what they call a quantum friction coefficient. And then that, of course, is the total friction is proportional to the velocity of the water that is flowing. And this classical term can be very intuitively understood. It's a function of the surface roughness and the structure factor of the water. So it's just literally stuff, the water bumping into the edges of the surface. The quantum term is a little more elaborate, but it essentially involves the overlap integral between the electronic excitation of the substrate and the dipolar excitations of the water. And so this is just really an overlap integral that you can calculate. And so the physical picture is that there is a velocity mismatch between the liquid and the solid, and this gives rise to the transfer of quanta of momentum, and this is why it's a quantum friction theory, and so it's really an electronic effect. Is essentially a surface plasmon, and that actually would account for the difference between the friction along graphite and graphene, because graphene only has an in-plane plasmon, but graphite also has an interlayer plasmon that provides an additional friction channel, which explains why the friction on graphite for water on graphite is so much larger than water on graphene. And those plasmons couple to low frequency modes of the water, so dipolar modes that just naturally arise in water. So this was all theory, and the question is how to prove it. And I'm an experimentalist, and so I wanted to talk extensively to Nikita. So how can we make this real? How can we prove it experimentally? Well, Nikita said it's interesting because you can show mathematically that this quantum friction that leads to this transfer of momentum at a finite velocity differential but zero temperature differential is equivalent to the transfer of quanta of energy when you have no velocity differential, but you have a temperature differential. So in other words, if momentum flows between the two subsystems, heat must also flow. Or if there is coupling that gives rise to quantum friction, the same coupling will give rise to heat transfer. And so Nikita then recast his momentum, so his friction, his quantum friction coefficient, which I told you has these electronic and water excitations in them. He recast that equation into an power per unit surface area transfer, which has a lot of the similar terms in it, and again has the same overlap of water and graphene excitation spectra. So now we go from momentum transfer to energy transfer, and it is fairly easy for us to, with our ultra-fast lasers, to induce short-term, very large temperature gradients or temperature differences in our system. So what we did is we built a cell, and we have now graphene on a glass substrate where we can expose it to water or not. And then with a very short optical pulse, we can do essentially a temperature jump experiment in the graphene, and actually the electrons we can heat up the electrons by thousands of degrees of Kelvin, but I'll show you that we don't have to go that high. And this is so the optical pulse heats the electrons. The hot electrons will cool. If there's no water, they will just cool by emitting phonons into the graphene. And then we can basically read out the quasi-instantaneous electron temperature in the graphene using terahertz spectroscopy. And I don't want to go into all the details of terahertz spectroscopy, but let's suffice to say that we know exactly how to correlate the difference in the differential of the terahertz pulse, so the change in absorption due to the optical pump, to the electron temperature. And so the question is very simply, I can measure the cooling of the electrons in the graphene without water, and then I add water to the system. It doesn't even flow. I just add water. It's standing still. Does that cooling rate change in the presence of water or not? So does the water provide an additional relaxation channels for the hot electrons? And if so, that would be consistent with the quantum friction. And so in this case, we're talking about the surface plasmon of graphene that is coupled to the low frequency modes of whatever liquid is in front of it. And to kind of more rigorously test the theory, we use different liquids. So we used H2O, D2O, methanol, ethanol, and isopropanol. And you can see all their spectra, their low frequency dissipative part of the dielectric function here, which incidentally is not non-trivial to measure. And then the coupling between those two is calculated here for H2O. And here you can see that there are specific frequencies where the graphene plasmon couples rather efficiently to the modes of the water. And so this is an experiment. So here is the change in the terahertz differential. At time 0 is when the optical excitation pulse heats the graphene electron, and then as we delay the optical excitation pulse relative to the terahertz pulse, we can see in real time the cooling of just graphene. And so we have photoexcitation, then we have very fast heating. So there's electron scattering that is occurring here in this red zone, and then in the blue zone we get cooling of the graphene, and so the Fermi level gets sharper again. And so again, in the presence of water, does this cooling speed up? So here are the experiments. So this is a room temperature experiment. The electrons, the differential in the temperature is about 300 Kelvin. We also did this for many other temperatures. And you can see that depending on whether there's nitrogen gas or H2O or D2O, there are slight differences in the cooling rate. It's a subtle effect, but it's significant and reproducible. And here you see the inferred relaxation rate. So these are simple single exponential fits to the cooling. And you see here that we have the case where there's no liquid in front of the graphene, so it's totally dry. And then when we add H2O, it goes, the cooling speeds up by about 20% or so, 15%. And this is the effect that we were looking for. Now, interestingly, as we go to heavy water and methanol and ethanol, the effect disappears again. And this is actually not completely surprising, because electron cooling in graphene requires that electrons and phonons scatter. And if you put a dielectric in front of your graphene, that will suppress those scattering effects. So we see a speed up for the water despite the screening of the interactions by the water. So this is very nice, and we see also that this effect decreases when we decrease the polarity. So there's a couple of questions. Why is there such a huge isotope effect? So why is the effect so much larger for H2O, right? It's this difference here. It's really twice as large as for D2O. And why does it change with polarity? Well, the theory captures what is happening. So in red, again, is the experiments. So in blue is the theoretical result. And you can see that when we calculate the contribution to the overall cooling rate due to the presence of liquid, it perfectly follows this trend quantitatively, and there's no adjustable parameters in this calculation. I think this is an important point. So the theory works, but why do we see this trend? Well, I told you that this liquid-assisted cooling rate is given by this overlap integral of the graphene plasmon with the liquid spectrum. But the graphene plasmon is kind of featureless, and so that the overlap between those two is really governed by the liquid spectrum. And so I did a very this is like my contribution to the work. I did a very simple analysis where I just integrated the low frequency spectra of these different liquids and correlated that with the calculated relaxation rate. And you can see that I get a very nice correlation between the two. And so the difference between H2O and D2O, and you can see that in the previous slide, is really the difference that you see here in the low frequency response of the two. So D2O is heavier, so these collective modes are at somewhat lower frequencies, and so there's less let's say density of states for the electrons in the graphene to couple to. And so water H2O gives the fastest relaxation, and that's precisely what we see here. So to conclude my second part, so it's really cool that this quantum friction seems to be a real thing. So there's kind of liquid-assisted electron cooling in graphene that reflects this. So this energy transfer is due to the same coupling that causes the momentum transfer, and we can then use the energy transfer method to basically test the coupling of electrons and hydrons. These are low frequency excitations in the liquid in front of the graphene. And so this is just, will come out soon in Nature Nanotechnology. So with that, I would like to end And thank you for your attention. And if you ever want to build your own water molecule, be careful with the ingredients because they are explosive. So thank you very much for your attention.
Thank you very, very much, Mischa, for the amazing talk and actually for showing us how complex is a simplest molecule like water. So now actually it's time to come up with questions from, first of all, from my two colleagues, Alice and Rong. Now, who wants to start?
Okay,
Rong?
maybe me. Okay, Alice. Okay. Thank you very much. Actually, I'm really, like this talk. It's amazing because I work on the microelectronics, actually, especially for the energy harvest. We use a lot of principles of triple electrical generator. So this liquid and solid, interface, you did so much, deep works. So it's really give me a lot of, kind of thinking. So actually, I have a question. First, I want to clarify that you use H2O is ODI water, right?
Yes. So it's
Okay.
actually so in the electrochemical system we have to you need some electrolyte, right? Otherwise it's the potentials are not defined. So there we typically use 1 millimolar of sodium perchlorate, but we can also use sodium chloride or any other electrolyte. So the story remains the same.
Okay, great. Actually, I have another question. Is in the second part you mentioned more about the physical, reactions, right? So this was major my concern about that because normally, we use this friction, as phenomena. So we want to pick up the energy. That time we consider more about, the frequency. For the moment, it's always in low frequency or something. So in your test, did you consider about all these kind of, frequency and the other parameters or issues?
Yes, that's a very good question. So I think there are different frequencies at work. And so for this quantum friction, it's relatively high frequency, right? It's in the terahertz range. And the reason for that is that otherwise you don't transfer sufficient momentum. So if the energy quanta get too small, the momentum quanta also just get very small. And so these are relatively high frequencies that are relevant here.
Okay, yeah. So to mine, of course, that's really too high.
Right. Yeah, that's what I thought. That's why I thought I would mention it.
Yeah. So, Ron, I have another question. Okay, yeah. So in your test, you talk about the surface, right? All this kind of because graphene single layers, all these things. Did you think like they have a skin? In the water, does it affect, how much, thickness of the skin? Yeah. So.
Yeah, this is also a very interesting question. So we actually did a lot of experiments also with different layer thickness. So, okay, I can give another half-hour talk about this,
Okay.
But I won't. So very briefly, yes, you are right. There is a certain depth over which the water feels the graphene. There's also a third by changing the number of graphene layers, we can at some point screen the substrate charge from the water. And then we get the real, let's say, the real water-graphene interface that we also see when we put a flake of graphene on top of deionized water. We get the same type of response. So the skin depth is typically very, very small. So it's really, it can be as large as a nanometer or a few nanometers, but this is rare. Typically,
okay, I see, understand. Yeah. Thank you. I like very much for that words. The water can feel the charges. Yeah, I like that words. Okay. Super. So yeah, finish, Paulo. Yeah.
Yeah, great. Thank you very much, Alice. Now it's time for Ron to come back with questions.
Okay, thank you very much.
Please.
Yeah, Michelle, I really enjoyed the talk a lot. For the
Thank
past
you.
hour, you share all the fundamental understanding of the water, like the charge, the friction. Yeah, I really enjoy it. Instead of asking question, I'm really very interested in the SFG technique because I personally am working on like the atomic layer deposition. So we are working on the solid gas phase interface all the time. So previously we indeed trying to use SFG to look into the monolayer growth or whatever. And later on, when we really trying to grow a film to cover the surfaces, we actually utilize SFG to understand the water movement within it, because like one of the application for our film is for the passivation. So I actually just starting this technique. So I would like to ask your advice or comments on utilizing this technique to understand the water permeation or penetration through like a different solid. Do you think that's a viable method?
I think yes, but it does depend on a lot of the details of the system that you're looking at. So let's say if you're looking at micron thick systems, it's going to be very difficult because you've very quickly re-enter this regime of centrosymmetry. So there will always be, if there's a water molecule oriented like this, there will be one that's oriented exactly opposite, and then the signals will cancel out. But there are certainly also sort of kinetic measurements of water infiltration into the type of systems that you mentioned, where actually initially you have a broken symmetry because the water likes to go in a certain way into the pores, and then at some point the signal vanishes because you get disordered random arrangement of water molecules. So it's certainly conceivable, but
yeah,
we can talk about this offline. Yeah.
Yes. Another thing that's associated with this is that because like the water, as you mentioned, that they have strong dipoles. But if in another case, if you have like, for example, hydrogen or hydrogen isotopes, they do not have dipoles. But when they associated with, like, for example, some surfaces or some like metals, they will become like metal hydride. Do you think like SFG technique is good for this type of thing? Although,
yeah. Okay. No, this works. This has been done. It's actually a long time ago. It was demonstrated that you can see metal hydride. So they have very high frequency, around 4,000 wave numbers.
Oh, I see.
But yeah, it's certainly possible. Yeah.
Okay. I think that's definitely a very interesting technique and a lot of fundamental with it. I think probably, yes, as you mentioned, probably we can talk offline about all this.
No, gladly.
Yeah, thank you very much.
Yeah, sure.
Yeah, Paulo. Yeah, that's my
Yes.
question. More looking into his advice because this is so interesting. I enjoy
it's very deep. Absolutely. Now, I actually have also one question that is related to this part of the SFG. You have not used as a remote control the change of temperature, which I guess it can scramble a bit all your system, in the sense that on the one hand, you get to disorder structures to the, a lot of dynamics, and to the extreme that you might also change a bit the distance, the intermolecular distances, right? So
yes.
Any wish of going to that direction, is that feasible? Is it as a kind of measurement, or is it too complicated? Have you done anything about that?
It's a very good question, Paolo. So this is certainly something we would love to do. The challenge of changing the temperature in steady state is that the experiments that we do require interferometric precision. So I make it look right, like you shoot one beam and shoot another beam, and then the light comes out. But it's a little more intricate than that. And so when you change the temperature, you typically automatically change path lengths of different beams, and so you lose the interferometric accuracy that is required. But what we're trying to do now is to essentially do the kind of temperature jump experiment that I showed you. We can also do that. So I showed it to you for the graphene side, but we can also do it for the water side, and then look at how we can look at non-equilibrium processes, but then also look at how what the state at the new temperature looks like in quasi-steady state. So that's the strategy we're going to follow.
Yeah, that's quite nice, actually. It is going to bring some interesting insight. Now, I have a second question that when just a bit later you showed about the idea of having protons that are tunneling through a graphene layer. How can you be sure that is a tunneling process? Have you tried any kind of attempt to study thicker, let's say, graphene flakes, such that, of course, you would have an influence on the tunneling process, since I guess this is so strongly dependent on the thickness of the barrier?
Yes, absolutely. So you're absolutely right that this tunneling rate, you could imagine that there are defects in the graphene and you don't actually have tunneling through the graphene, but you have transport through the defects and then spreading out along the calcium fluoride graphene interface. So we were on the lookout for that, let's say. So the one indication that defects do not play a huge role is that it didn't matter what graphene we used or what position we are on a specific graphene. We always get the same time constant. So that's very reassuring for this transport. And indeed, when we put multi-layers, when we put 2 or 3 layers of graphene, it slows down in a way that is consistent with the tunneling barrier increasing through the material.
Okay, interesting, very interesting. All right, so Alice, is there any question?
I got a question from my previous PhD. Is doing some energy harvesting for harvest the energy from the ocean. It's asking for is this can be studied for like these salty waters and different waters for this? Professor Mischa.
This is very, very interesting question, right? About harvesting osmotic energy. And yes, we can certainly investigate the interface of, say, an osmotic membrane and water and different degrees of salinity. There's nothing that speaks against that.
Okay, so do oils, right? If it's oils or this kind of solution, all can be studied by this.
Yeah.
Thank you
so
very
we've
much.
So we've also used it for ionic liquids, for instance. So to look at the surface of ionic liquids.
Okay, great. This is very, very useful and open a window for the people from all these kind of, the sensors part, all these kind of engineers to look more into the science part.
This is, I think, also why I'm excited about the work, because there's a lot of the technologies that are related to water are developed through trial and error, or people just find that something works. I've also done that, of course. You make discoveries, but more out of chance than by design. And so I think it would be very nice to understand really the fundamentals, to try to get a bottom-up understanding of these types of complex systems.
Yes, right, exactly. Now we need, if we understand that we can get all these devices more controllable, the quality can be, optimized very much.
Yeah, I hope so.
Okay, thank you. Yeah. So Paula, yeah, maybe
Perfect.
I going to, yeah, because today we not only, have this wonderful talk, we also
Yes,
welcome
absolutely.
our new partners. Yeah, I'm so excited. Yeah. Now I'm going to, ask some questions for you and Ron. Maybe Professor Moshe, you also can ask, can tell us what you want us to do. Okay. Yeah. My first question is for Paulo. So I think now, yeah, of course, welcome very much. And you already invited wonderful speakers like Professor Moshe on this stage. So as a new partner, and I can ask very well now. And yeah, what do you think you want to do, for ICANX in the future?
Well, that's a very, it's not easy question to answer, but I mean, in my opinion, there are two directions that I like to contribute with. The first one is actually on the emergence. Okay, so we really have the emergence of the young researcher and also diversity. I mean, having really contribution from all five continents. Okay, so that is actually what we might also get even better than what we have at the moment. And in particular, I think the second event on the young people, that is key. It's really key, and I really want to help there. And the other issue, in my opinion, is that we really, as I think is well done in some part of the world, but not in all the parts of the world, is to keep a very strong eye on the global impact on topics that will really change our way of living. Okay, so and what we have to face. So that I think I will try to help to push our contribution and our understanding on the fundamental science that goes toward those kind of applications. So that is what hopefully we will be able to do even better in the years to come.
Okay, great. I visited your lab. I mean, it's like a United Nations, you got the peoples from all over the world. Yeah, different paths for sure. Yeah, we're looking forward to have more and more, peoples from a different, place and to show, especially the young people from, different part of the world need to get more pressure on that, yeah, more showed up and highlight on this stage. Yeah, I totally agree with it. I'm looking forward to have more, from you graduated from the oldest university, right, in Italian.
Yes.
Yeah, the oldest one. So I mean, you may have a more experience, how to handle, how to work with all these people. So that's super. Yeah, looking forward to that. June, how about you?
Yeah, I definitely think the ICANX has been sort of expanded to a lot of countries and a lot of regions in the world. I think that is definitely one of our pushes there. The other things I totally agree with Paulo is that just like today's talk, I think it's definitely inspired a lot of related fields. Although I could not understand many of the equations Michelle talked today, but it's actually inspired me a lot of things. No. I think it's definitely very helpful. I agree a lot with Paulo. That's the fundamental talks. Definitely one of our pushes. Big names, fundamental talks, good work. Yeah, I like it. The other thing is just so Alice is trying all her best is to get all the young peoples as well as a lot of females on board. I think that's definitely one of the good things for us.
Yeah. So, Ron, now you are really a supermodel for many young, female scientists. Yeah. I think in your experience, what's the most kind of usable part or supportable part, in your career? So if you can tell us this, maybe we can do more.
No, I think Alice, you have already done a lot of good things. Basically, just promote as you tried all your best that every of the ICANX talks that you want to have at least one females. Either they could be ex-challengers, they could be panelists or moderator, whatever. But yes, you definitely get the diversity there. Thank you.
Okay, yeah. So, yeah, try our best. So, Professor Mischa, yeah, you know that now in the society, academic society, we really need to promote the young scientists, the female young scientists, yeah, because we need a bigger pool, right? Yeah,
Yes,
then the
absolutely.
people can be grow up, yeah, sure.
Yeah, and I think so. What I notice is that women attract women, right? If you have women in leading positions, more women join science, and so it's very important. Yeah.
Yeah, so we really, put some efforts here, like every flyer of this, either young youth talks or I can act talks, we at least have one female.
That's great. Yeah.
We have a
I would like
certain.
to. I would like to stress the correlation of what Mischa just said. That said, women attract women, and actually, he has been talking about forces and dipoles during his talk. So I really see a strong
Absolutely.
link. I mean, this is said by someone that is expert in the field, right? About
Yes.
interactions.
Yes.
Thank you so much for this. Yeah, so Professor Mischa, now you get on I Can Act. How did you feel and what you want us to do more?
I think this is a fantastic initiative. I really think it's unique worldwide. And I mean, who am I to give you advice on how to do this? I think you're really doing a fantastic job. You're exposing people to top science. You're involving the young generation. I think that is very important. You're really a fantastic advertisement for diversity. So 2 thumbs up.
Thank you. Thank you very much. Yeah. So I also have a lots of question for our, partners, our new partners. Okay. Paulo, I say that you, covers, many places, right? Yeah, not only different countries, right? Maybe different continentals, right? Yes. Yeah.
Absolutely.
So you know most about the people, in your area. So did you have any idea how to reach out to the peoples not in your area, not in your field, so to reach to them? Did you have any thinking about this?
Well, I think we have to be creative there. It's not the easiest challenge that one can tackle. I think the new media that we are able to use nowadays, that really allows to expand also our, let's say, information networks to what goes beyond our classical pool of friends, colleagues, and in our field. So that's probably what one can best use. But I mean, the number that you have been reaching with this ECANX are such that I think is unbeatable. I mean, of course, there is always room for improvement. By starting from an amazing, let's say, success that you already had reached in the last 2 years,
Okay, good. Yeah. So, Ron, how about you? So, any ideas we reach out to, the people's not maybe, very close to our field, even in, different kind of emerging fields like that?
Well, I think that's definitely challenging. But through the network, probably, I mean, right now we are able to have conferences, have some physical interactions, and also we have have this type of network that we are having more of the young teachers and the young many of them may bring their students or sort of trying to spreading this out. And another thing I think is quite important is like for this INX platform, we actually invite scientists from all different fields. It is also an interdisciplinary interactions, and this is quite unique. And I mean, I can always learn something new, and I feel that those people will get the same kind of ideas. So I would think that's just trying to get more good talks and trying to bring more people. That's probably the way I would suggest, and I would try to my best to promote that.
Okay, counting on all of you. Okay, yeah. Like today, Professor Mischa's talk really gave us a lot of thinkings. Though we are not working, in your field, but your research really inspire us. Yeah, that's very, very important. So, Paulo, now I'm going to share the,
Sure,
share
the
the
slide.
slides. Yeah. Okay. Yeah. That's your 10.
Perfect. So here we are. Great. So this was today. This was actually what we were delighted to see today, the miraculous water molecule and how complicated or how complex this molecule is. But we after this amazing talk, we will go further, right? Can you click the next slide, please, Alice?
So did you see this one? Yeah. So
Yeah,
we're going
absolutely.
to. Okay. Cool. Yeah.
Perfect. And actually, so what's next? Next is going to be so the talk on the green data communication. The next challenge after 5G. This is going to be given from a German colleague, actually from Technical University in Berlin, Dieter Bimberg. So this will be a very interesting talk, again showing how broad is the focus of ICANX. And there will be also distinguished panelist and moderator. That moderator is actually here with us today, Rong. And we also will have a challenger next time. So that is going to be extremely interesting. So that's going to be next week. And now actually, I think we are just here to applause today's event. So to stress the importance of this democratization of science that Alice has been able to build up through ICANX talks. And yes, Alice, so the last word is yours.
Okay, yeah. So actually last week we're going to, have a more fun because not only the online talk, but we're also going to have another offline, see the people in person. We are going to go to Xi'an, have a ICANX Xi'an summit to get the scientists go together. So that will be more fun. We're going to have more friends and listen to more talks. Okay, thank you very much. A wonderful night. Yeah, or maybe a wonderful day. Super. Yeah.
Thank you very much.
不再是情，不再是幻想，此刻真感觉全世界为我鼓掌，不必太在意身旁惊奇的目光，点头可以放声歌唱，我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。I can。没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。 造奇迹。我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有谁